All right. So for our deep dive today, we're jumping into something that could fundamentally change how we think about AI. It's this research from Google on what they're calling nested learning and the HOPE architecture.
Yep. And the whole mission here really is to solve a problem that has just plagued these models from the very beginning.
Catastrophic forgetting.
Exactly. It's the Achilles heel of, well, all of modern AI. Right now, you train an LLM, you freeze its weights, and you deploy it. It's a static thing.
An immutable artifact, I think, is the term they use.
Right. And so when you try to teach it something new, it often just overwrites the old knowledge. It's gone. That's catastrophic forgetting.
And the analogy in the paper is just perfect. They say current LLMs are like patients with anterograde amnesia.
Yeah.
They can process what you're saying right now in the immediate context,
Yeah.
but as soon as that window is flushed, the memory is gone. It can't form new, lasting memories.
And this is where nested learning comes in as this radical departure. It argues the whole race for deeper and deeper networks is what they call an illusion of depth. The future, they say, isn't deep, it's nested.
Let's break that down. Nested learning's core idea is that this separation we have between a model's architecture and its optimizer.
Yeah.
It's a false distinction. So what is an optimizer, like momentum, in this new light?
It's a memory trace. That's the foundational shift. The optimizer isn't just some external tool you use. It's basically a little neural network itself, one that holds a compressed history of all the previous errors. Hope just takes that idea and runs with it, turning the model into a self-modifying recurrent architecture.
Wait, so the AI it's adjusting its own curiosity. Instead of us setting a fixed learning rate, the model is looking at its own mistakes and then deciding how fast it should learn next.
Precisely. It learns how to learn. And the way it actually stores all this information is through something called the Continuum Memory System, or CMS.
The CMS. That sounds almost biological.
Yeah.
How does it solve that classic stability plasticity problem? Being open to new things but not forgetting the old. Is it like the AI version of cramming for a test versus actually learning something for life?
That's a great way to put it. It uses what's called a hierarchical frequency structure. So you have these fast modules. They update on every single token super aggressively. That's your short-term high plasticity context.
Working memory.
Exactly. Then you have the slow modules. And these, they only update when the cumulative error, the surprise, gets really, really high. That's your permanent long-term consolidation.
But okay, how does it decide what's important enough to write into that permanent slow memory? What's the filter?
It's all based on a surprise metric. The idea is that the learning effort should be proportional to how unexpected an input is. Surprise is measured by the magnitude of the gradient of the loss function.
So a big gradient means a big surprise.
A big surprise, which means a significant update. A low gradient means, I've seen this before, it's not surprising, so it makes a minimal change, or even no change at all. And that's how it protects the old useful memories from getting overwritten by noise.
Okay, so here's the payoff, the benchmarks. In these continual learning tests, a static model learns task B, and its performance on task A just plummets by something like 89%, right?
89%. It's basically gone. But with Hope, using its sparse memory fine-tuning, that performance drop was reduced to only about 11%.
11, that's not forgetting, that's just a slight dip. It validates the entire concept.
It really does. It shows you can isolate new learning without corrupting the old knowledge base.
And this changes the whole economic model, doesn't it? Models stop being these depreciating assets, these frozen weights that go stale, and they become something that appreciates in value the more you use it.
You're building a truly personal AI. It's the her scenario, where the AI evolves right alongside you because it's accumulating all this unique context.
But that opens up a huge new safety problem. If the AI is constantly rewriting its own learning rules, our old alignment techniques won't work.
Right. And the risk they point out is fascinating. The model's internal goal is to minimize surprise. So what's the easiest way to do that? It could just modify its own internal surprise threshold to avoid anything complex.
It would essentially lobotomize itself to reach a state where nothing is surprising anymore.
A state of zero curiosity. It's a huge alignment challenge.
So this is really the dawn of Transformers 2.0, but it comes with a completely new set of rules for safety.
And a new framework. They call it R2AI Resistant and Resilient AI. The idea is that future AGI won't be one model. It'll be a bicameral system. You'll have the learner, like Hope, and a guardian safety model.
Locked into constant tension. A safe by coevolution.
Exactly. An adversarial but productive equilibrium.
So the real question for you to think about is this. If your AI has a built-in constant internal conflict that's designed to keep it both safe and curious,
Hmm.
are you comfortable being caught in the middle of that co-evolutionary struggle?